Welcome to the 15th session of the Vykhari International Lecture Series 2021, organized by Bishop Cholaparmil Memorial College, Kottayam. Vykhari means a journey of sound or speech and dissemination of knowledge through words. For BCM College, Vykhari is an annual lecture series started during the Diamond Jubilee of the college in 2015. This year, Vykhari Lecture Series is an international lecture event started on September 14. Welcome to today's session of this lecture series is in mathematics, and the resource person is Dr. Rajesh Kannan, Assistant Professor in Mathematics, Indian Institute of Technology, IIT Kharagpur. The title of the lecture is Laplacian Matrices and Their Applications. Let us start with the blessings of God. I invite Ms. Anina Thomas of third year BSc Mathematics for the prayer song.
They shall be showers of blessing. This is the promise of love. They shall be seasons refreshing, sent from the Savior above. Showers of blessing, showers of blessings we need. Mercy drops round us are falling, but for the showers we play. They shall be showers of blessing, precious reviving again, over the hills and the valleys, sound of abundance of rain. Showers of blessing, showers of blessings we need. Mercy drops round us are falling, but for the showers we play.
Now, I invite our head of the Department of Mathematics, Ms. Anne Jones, for the welcome speech.
Good morning to one and all. Respected College Principal Dr. Steffi Thomas, distinguished Chief Guest of the Day Dr. Rajesh Kannan, dear HODs, faculty members from various departments, HODs from various departments, participants from various institutions, dear colleagues and my dear students. Vykhari, meaning dissemination of knowledge through words, is the annual lecture series of Bishop Cholaparmil Memorial College, started in the year 2015. Through this platform, the thoughts and knowledge of various eminent personalities like former governors, DGPs, ambassadors, etc. enlighten the minds of many. This year, Vykhari is organized as an interdisciplinary international webinar series incorporating 17 lectures of top flight professors all around the world. First of all, I invite our dear principal, Dr. Steffi Thomas, who is a part of our department and a real motivator behind this webinar. I welcome you, sir. Today is the 16th lecture series, and we are honored to have Dr. Rajesh Kannan from IIT Kharagpur to present this section. He is a constant well-wisher of our college, having great values and work ethics. His focus to pursue academic excellence is quite evident from his career profile. I still remember his mind-provoking address during the international conference ICGC 2020 conducted by our department. On behalf of the Department of Mathematics, Bishop Cholaparmil Memorial College, I wholeheartedly welcome you, sir, to this lecture series. At this juncture, I welcome our college Vice Principal, Dr. Annu Thomas, our Bursar, Reverend Father Philmon Kalatra, HODs from various departments, faculty members from our college and various colleges, research colleges, students from various departments in and out Kerala, and my dear students. I welcome you all. Wishing you all a most fruitful section. Have a nice day. Thank you.
Thank you, Professor Ann. Now it's time for today's session. Our speaker is a renowned speaker in mathematics, Assistant Professor in Mathematics at IIT Kharagpur, Dr. Rajesh Kannan. He has completed his doctoral research from IIT Madras with the Professors Veeramani and Professor Shivakumar. He has plenty of publications in various international journals. He is currently a research guide, and he is organizing a very well-known lecture series in spectral graph theory, which is ongoing with about 64 lectures at present. Hearty welcome to Bishop Cholaparmil Memorial College to you, sir, and I have hearty welcome to deliver this lecture. Over to you, sir.
Yeah, thank you. Thank you so much. Okay, good morning to everybody. Yeah, first of all, I would like to thank the BCM College for the invitation, the department for the nice introduction. Yeah, so title of my talk is Laplacian matrices and their applications. So first I will share my presentation. Okay, I think we'll use. Can you see my screen now?
Yes, sir. Yeah.
Okay. Yeah, title of my talk is Laplacian matrices and their applications. So I think most of you have done a course on graph theory and linear algebra. So I will just assume basics of graph theory and basics of matrix theory. Okay. And whatever terminology I will be using in this talk, I will be defining everything rigorously. Okay. So this is the outline of the talk. I will start with the problem, which is the graph partitioning problem, which appear in graph theory. And we'll see that this problem is not an easy problem to solve from computational complexity point of view. Then we will see a method, an approximation method, which will give you a kind of solution to the given problem. Okay, some efficient solution we can say. Okay, using the eigenvalues and eigenvectors of Laplacian matrix associated with the given graph. Okay, so I have mentioned applications. I have two applications to present. If time permits, I will go for both the things. Otherwise, I will stick to first application. Okay. Yeah. Before that, how much time I can take, Dr. Anu?
I can take 1 hour, sir.
1 hour. Okay. Good. Okay. So let us start with the problem. So the graph partition problem as per this. You take a simple weighted graph. Okay. So just start writing. So a graph G is given by V comma E. V is the set of all vertices and E is the set of all edges. Okay. So we'll assume this graph to be a simple graph. That means we don't have any loops or we don't have any multiple edges. It's a weighted graph. Okay. So weighted graph means every edge of the given graph will have some non-negative weight. Okay. So for this type of graphs, we have to find a partition of the vertex set satisfying some properties. Okay. So what are they? So first, let us define what is a partition. Okay. The graph partition problem is the following: we have to find out a collection of subsets V1, V2 up to Vk of your vertex set V, such that when you take the union of all these sets V1 up to Vk, this should give you entire V, and the elements of this collection V1 up to Vk, they are disjoint. Okay, they are pairwise disjoint. that is VA intersection VJ, is empty whenever I is different from J. Okay, so basically, if you draw the collection of all vertices in this diagram, then V1, V2 up to Vn, just a partition of Vn up to Vk is just a partition of your vertex set V. Okay. Yeah, if I'm not clear, then please stop me. Okay, and whatever doubt you have, you can stop me at any point. Okay. Okay, so now we impose one more restriction on this partition. We don't want to partition the vertex sets in arbitrary way. Okay, so we want to impose a balance constraint. So balance constraint means cardinality of VAs are almost same. Okay, so this notation, this single line here and single line over here, this stands for the number of elements in the set VA. Okay, and needless to say, we are working with only finite graphs. By finite graph, we mean number of vertices is finite. Okay, so now we are partitioning the vertex set of V into k parts, and the balance constraint says that you have to partition the vertex set in such a way that the number of elements in each of the VA is almost same. Almost same, we mean maybe cardinality. If you take two different sets VA and VJ, then the difference between their cardinality is at most 1. Okay, that is either cardinality of VA equal to cardinality of VJ, or cardinality of VA is equal to cardinality of VJ plus minus 1. Okay, so you can roughly think like that. Okay, so more rigorously, this quantity can be read out in this way. So if you consider graphs whose all edge weights are equal to 1, then the balance constraint can be stated in this way. Okay, for some epsilon, for some small epsilon. Okay, cardinality of VA is less than or equal to 1 plus epsilon time cardinality of V by k. Take the scaling function. Okay, so now you can see this cardinality of V. It need not be a multiple of k. Okay, so when you divide when you divide V into k parts, you cannot expect all components, the VAs, to have same number of elements. Okay, so basically, like we want so how much we can be close to the equal partition. Okay, when it is not possible to partition equally. Okay, that's all about the balance constraint. Yeah, so I need one more terminology. Okay, so I've done a course on graph theory, it should be familiar to you. So given two vertex subsets VA and VJ, okay, so you consider we will define this EIJ. Okay, EIJ of VA VJ. So hereafter I will simply write EIJ. So EIJ stands for collection of all edges in your given graph G. Okay, such that one end of that edge is in VA and the other end is in VJ. Okay, so if you have VA is sitting inside G. Okay, this is your entire vertex set. If this is your VA, then you are considering all the edges between the sets VI and VJ. You are considering the graph may have oops. Yeah. So V contains both VA and VJ. Okay. So we consider collection of all edges between the vertex sets VA and VJ. Okay. And W of EIJ is the sum of the weights of the edges in EIJ. Okay. So all these edges, all the edges between the VA and VJ, they do have some weight. You have to add all the weights. Okay. And that weight, the added weight is called weight of EIJ. It is denoted by W of EIJ. Okay. So now let us state the problem. The problem is to find out a vertex partition, okay, V of size k, such that when you compute the sum of the weights of EIJs, okay, this should be minimum. Okay, so you will be partitioning this V into k parts, V1, V2 up to Vk. Okay, so now you compute this EIJ for various I and J's. Okay, so EIJs for I less than J, then compute their weights. Okay, take the sum. So we need to find out which partition, okay, will give you a minimum weight. Okay, so this type of problems occurs in many applications. So I will not go into that. Okay, so how to solve this problem? So complexity of this problem is NP complete, even for balanced bipartition. By balanced bipartition, I mean, so you have a graph and you have to just partition. You have to partition your vertex set into two parts, okay, and you have to find out a let's say bisection. Okay, bipartition may not be right, but bisection of your vertex set, your vertex set. Okay, and you have to find out the minimum bisection corresponding to this quantity. Okay, or a bisection which gives you the minimum value for this quantity. Okay, so that is our that's the ambition in case of k equal to 2. Okay, or simply k equal to 2 you take in this problem. That's the problem I want to consider. Okay, so if you know about computational complexity, this problem falls into NP complete category. Okay, this is one of the hardest problem to. It is not an easy problem to solve. Okay, so naturally from complexity theory point of view, if you don't know or if a problem is a hard problem to solve, or NP complete problem, then we will go for some approximation methods. Okay, so one of the approximation methods is given by the spectral approximation or spectral methods. This is one of the developing field. Okay, yeah, there are a lot of interesting results are there in this field. So today I'm going to present one such result. Okay, okay, is it clear? This is the problem. So we want to address this problem using this spectrum of the using spectral methods in the graph theory. Okay, if it is clear, then let us move on to the content of today's lecture. So if you are given a graph, okay, one can associate many matrices with a given graph. One of the very naive class of matrices associated with a given graph is the adjacency matrix. Okay, if you are having a graph on n vertices, then adjacency matrix is a matrix on n vertices. Okay, whose rows and columns are indexed by the vertex set of your given graph G. Okay, and the ijth entry of the matrix A is given by okay, so ijth entry of your matrix A, the adjacency matrix is given by it's equal to 1 if the vertices I and j are adjacent. Okay, this will be 0 if they are not adjacent. Okay, so if between the vertices I and j, if there is an edge, then we will keep 1 in both the ijth position as well as jith position. Okay, so let us see an example. So you consider this simple graph. Okay, the adjacency matrix of this graph is given by so it's a graph on 4 vertices. So the associated adjacency matrix is a matrix on 4 rows and 4 columns. Okay, so ijth entry. So here let us focus on the first row, the 1th entry. So we are working with simple graphs, so we don't have any loops. That means we don't have any edge from the vertex 1 to itself. So the diagonal entry, the first diagonal entry is equal to 0. If you apply the same logic to rest of the vertices, we can see that all the diagonal entries should be equal to 0. Okay, and I will explain only for the first row, and rest of the rows you can fill on your own. Okay, now you focus on the 1/2 entry. So first row, second column. Okay, so between the vertices 1 and 2, you have an edge here. So we put 1 here. And between the vertices 1 and 3, there is an edge. So there's a 1 here. And between the vertices 1 and 4, there is an edge, and we have 1 here. Okay. As it's an undirected graph, so whenever you have an edge between 1 and 2, that means you have an edge from 2 to 1 also. So you can fill this matrix symmetrically, okay, in this way. I'll explain only one more term. So here you see 2/4 term between the vertices 2 and 4. There is no edge, so we are having okay, so only this part, this 0 you focus, only this 0. Yeah. Because there is no edge between the vertices 2 and 4, so we are putting a 0 here. Okay, so in this way you can fill your graph. You can fill your. So question for me. Okay. Great. Okay, so the next class of matrix associated with the graph is the Laplacian matrix. Okay, it's closely related with the adjacency matrix. How it is defined? Okay, so let us take a simple graph with the vertex at 1 to n and it's at u1, e2 up to em. Okay, the Laplacian matrix is an n by n matrix again, whose rows and columns are indexed by the vertices of your given graph G. Okay, how it is defined? Okay, the rows and columns of L of G are indexed by V of G. If I is different from J, okay, the ijth entry of L of G is 0 if the vertices I and J are not adjacent. Okay, and it will be -1 if the vertices I and J are adjacent. Okay, and the diagonal entries of the L of G is given by di. Okay, the di stands for the corresponding degree of the vertex I. Okay, so this definition can be nicely rephrased in terms of adjacency matrices as follows. So how to phrase that? So let us define a diagonal matrix first. By diagonal matrix, we mean it's a matrix whose diagonal entries are all off diagonal entries are 0. Okay, the possible non-zero entries will be sitting on the diagonal. Okay, so for a given graph, the degree matrix, okay, it's a diagonal matrix. It's denoted by d of g, whose diagonal entries are given by the vertex degrees of your given graph. That is, ith diagonal entry is given by the degree of the ith vertex. Okay, if we denote that matrix by d of g, then the Laplacian matrix, what we defined in the previous bullet, that is same as L of g equal to d of g minus a of g. Okay, so this you can convince yourself these two definitions are the same. Okay, so one point. Okay, so again let us focus on the example. Okay, just if you see this a of g, d of L of g equal to d of g minus a of g, that representation, then you can see that the off diagonal entries are coming from the adjacency matrix. Okay, just to negate the entries of the adjacency matrix, and for the diagonal entries, just keep the degree of the particular vertex. Okay, degree of the corresponding vertex. So first vertex has degree 3, so we keep 3 over here. Okay, so this is one of the very naive matrix associated with the given graph, but it contains a lot of combinatorial information about the underlying graph. Okay, that is one of the main theme of spectral graph theory. So if you want to study some of the properties of the graphs, then we can associate a matrix with or a class of matrices with the given graph, and using the eigenvalues of the associated matrices, we can say something about the structure of the graph. Okay, or some of the combinatorial properties of the graph. So today we will see one such property. Okay. Yeah. Before that, let us see some of the basic properties of Laplacian. Okay. So if I take a simple graph G with the vertex at 1 to n and it's at E1 to Em, okay, then the row sums and the column sums of the Laplacian matrix L of G are 0. Okay. The reason is the way we have defined the Laplacian. You see, we kept the degree of the vertex in the, if you are working with the ith row, okay, we are working with the ith row. In the ith row, the diagonal entry we kept the degree of the vertex, okay, ith vertex. And off diagonal entries, you see how many -1s we had. We had -1 for -1 for each adjacent vertex. Okay, so totally we have dA number of vertices which are adjacent to the chosen vertex I. So naturally the row sum will be equal to 0. As it's a symmetric matrix, so you will get the column sums also equal to 0. Okay, so equivalently, if I so this will be useful in many of the problems. If I denote okay, yes, if E stands for all ones vector, okay, if I denote E for 1 1 1 1 1, okay, if you want to apply transpose, then you take the Laplacian of G and E. So this is nothing but what will happen. So just look at this matrix vector multiplication. If you had to find out the resultant vector over here, the first entry of this vector L of G into E, what is that? You take the first row and multiply with this vector E. Okay, so scalar product of first row with E. This E, you see, you can see that the role of the vector E in this multiplication is this is just summing all the entries of your row. Okay. So here you will get 0 0 0. So that is this, you can think of 0 into E. Okay, So if you have done a course on matrix theory, you can realize that the 0 is an eigenvalue with the E is an eigenvector of the Laplacian. Okay. So the row sums and the column sums are equal to 0. That gives some more information about information about the eigenvalues of the given graph. Okay, at least 0 should be an eigenvalue, irrespective of whatever graph you are choosing. Okay, 0 is always an eigenvalue. Great. So next property, this is one of the very crucial property. Okay, you choose any vector x. Okay, that then you focus on this quadratic form, x transpose L of G into x. Okay, so x transpose is an 1 by n vector, L of G is an n by n matrix, x is an n by 1 vector. So this is a scalar. X transpose L of G into x is a scalar. So this quantity is given by this summation xi minus xj whole square, where the summation runs over all the vertices which are adjacent in your given graph. Okay. So this quantity is one of the very most important quantity. So one thing is, namely, if you look at this quantity, what does it say? If you compute the quadratic form associated with the Laplacian L of G corresponding to this vector x, then this quadratic form measures something like the variations in the vector x. Okay, so variations among the components of your vector x with respect to the graph G. Okay. Maybe some of you are research scholars attending this seminar. There is a recent notion called spectral spacification. Okay, so spectral spacification is kind of you have a dense graph, okay, large dense graph. So you want to approximate. When you are working with large dense graphs, it is difficult to work with those graphs, because if the number of edges are more, then it is difficult to compute eigenvalues and all. Working with those type of graphs is a little tricky. So recently, I think Dan Spielman and his collaborators they have proposed a concept of spectral spacification. Okay, so this quantity x transpose L of G into x, this plays the crucial role in defining the spectral spacification. Okay, using this quantity, they have defined the notion. That's one of very interesting topic. If you are interested, you can go through. I will give you some references. You can go through over it. Okay. Yeah. So if these two properties, okay, if the second property, if you consider it to be true, or if you accept the property, then the third property is simply a consequence of second property. Okay. How? L of G is symmetric. The way we have defined the symmetry is clear. Okay. So positive semi-definite matrix. You see, to show a matrix is a positive semi-definite matrix, you have to show this quadratic form is non-negative. Okay, for every vector x. But this representation x transpose L of G into x is equal to sum of squares. Okay, so it will be always a non-negative quantity. So sum of non-negative numbers, you will get always a non-negative number. So L of G is a positive semi-definite matrix. Okay, so I have included a proof for the second statement. Okay, but I will not read the proof. Just the presentations will be available to you. Just try to read the proof. Okay. You will get the proof. Just this is purely algebraic manipulation. Okay. Okay. So before moving on to the application, let me tell you one of the exciting property of the eigenvalues of the Laplacian matrix. Okay. So this theorem justifies the name spectral graph theory, I would say. Okay. So why? So you have you take any graph G. Okay. You consider its Laplacian, okay, L of G. So Laplacian is a matrix. So rank of a matrix is a meaningful concept. Okay, so how many linearly independent rows is the matrix has? Okay, that's the definition of rank. If we take this quantity should be equal to n minus k, where n is the number of vertices of the graph G and k is the number of components of your given graph G. Okay, if the graph is not connected, then you can count the number of components in the given graph. Okay, if it has k components, then rank of L of G is equal to n minus k. Okay, so what is the beauty in this result? See, in one side, rank of L of G. So rank is a purely linear algebraic quantity. Okay, so this quantity is equal to n minus k, where n is the number of vertices and k is the number of components. This is a graph theoretical quantity. Okay, So this theorem is connecting a linear algebraic quantity, okay, with the graph theoretic quantity. Okay, so these types of results are celebrated in spectral graph theory. Okay, so this result was proved by Fielder long back 1970s. Okay, in fact he did more. I will just briefly tell after completing the proof of this theorem. Okay, okay, is the statement clear what I'm trying to say? If you have any question, you can ask me now. So this is the only theorem I am going to prove in this lecture. Okay, then we will move on to the application part. I think the statement, is it clear? So you take the Laplacian, rank of the Laplacian is equal to n minus k, where k stands for the number of components in G. Okay, so if you assume this theorem, suppose if I say the graph is a connected graph, then what is the rank of your Laplacian? Maybe you can just type in the chat box. If the graph is a connected graph, then what is the rank of your Laplacian? Maybe those who are in BSc and MSc, you can answer.
You can write the answers in the chat box.
At least one? Yeah, great. Yeah, n minus 1. Okay, nice. Yeah, let's proceed. The proof is really simple. Okay, we will enjoy. So let us prove this result on using the on the number of components. Okay, so what do we mean by that? First, let us consider the case k equal to 1. Okay, that means your graph is connected. Okay, it is clear that 0 is an eigenvalue. Okay, the argument I already gave. The reason is if you take the vector E, okay, to be all ones vector, then LE equal to 0 into E. That means 0 is an eigenvalue with the all ones vector as an eigenvector. Okay, great. So rank should be at most n minus 1. Okay, it has 0 as an eigenvalue. Okay, and as we are working with a symmetric matrix, the multiplicity of 0 as an eigenvalue. Okay, if you know that, then you can tell about the rank of the matrix. Okay, so note that in general for arbitrary matrices, this result need not be true. So what is that? The multiplicity of 0 and the rank of the matrix. You may expect some natural connection. Okay, if your matrix is not a diagonalizable matrix, then that will not the connection need not be true. So to be precise, what I'm saying. So if okay, so if 0 has multiplicity k, then we cannot claim the rank of the matrix is n minus k in general. Okay, so that's true for diagonalizable up to diagonalizable matrices. That result is true. Okay, if you take a non-diagonalizable matrix, then the result need not be true. The obvious example or the easiest example is you take this matrix 0, 0. Yes, yeah, this matrix will work. So, so this here you take the eigenvalue 0 has multiplicity 2, but still this matrix has rank 1. Okay, this is not a diagonalizable matrix, so that's a natural expect. So that result need not be true. That's what I want to say. Okay, as we are working with symmetric matrices, we will not encounter this type of problems. Okay, so what I'm trying to say. So if 0 is an eigenvalue, then the rank of the Laplacian will be rank of the L of G will be at most n minus 1. Okay, so now I want to show algebraic multiplicity of 0 equal to 1. Okay, so as it's a symmetric matrix, so it's diagonalizable, so it will imply that the geometric multiplicity is also equal to 1. Okay, or I will show that you will get up to constant multiple, you will get exactly only one eigenvector corresponding to the eigenvalue. Okay, I think I should have told in the reverse way. Okay, so you will get only one non-zero eigenvector up to constant multiple corresponding to the eigenvalue 0. Okay, so that is completely coming from the graph structure. Okay, so if x is an eigenvector corresponding to the Laplacian of the Laplacian L of G corresponding to the eigenvalue 0, okay, then Lx should be equal to 0. Okay, so note that I'm not writing again L of G again and again. I'm writing here L instead of L of G. So if x is an eigenvector corresponding to the eigenvalue 0, then Lx is equal to 0. So x transpose Lx should be equal to 0. Now you apply that equivalent representation of this quadratic form x transpose Lx in terms of the sum of squares, okay, where the summation is guided by this adjacency list given in the graph. Okay, so this sum is equal to 0. So now you see this is sum of some non-negative real numbers that is equal to 0. That means that each term inside this sum should be equal to 0. Okay, so that is same as whenever the vertices I and j are adjacent, okay, you will get xi equal to xj. Okay, as we are working with a connected graph, between any two vertices you will get a path. Okay, and on any path, if you apply this argument inductively, you can show that if you take the eigenvector x, if you look at the components of the eigenvector along any path, okay, along any path it should be constant. Okay, that's what I have written in the next line. Okay, so between any two vertices you will get a path. Okay, and the component vectors of x corresponding to the vertices in the paths are equal. Okay, just an induction argument will work. Okay, so just this, you take the base case of your induction, and then you can prove it for vertices which are not adjacent but they are connected. Okay, they should have same component. Okay, so that proves that as the given graph is connected between any two vertices, you will get a path. Okay, so you can think of, you can fix one vertex as a root, and then maybe you can travel to rest of the vertices via some paths. Okay, so if you keep some non-zero value for the root vertex, then for all the rest of the vertices they will have the same value. Okay, if the vector x is an eigenvector, that means it is just a constant multiple of your vector e. Okay, so that means that the eigenvalue 0 has geometric multiplicity 1. Okay, so only the multiples of the constant vector e, those are the only possible eigenvectors for your given graph. So geometric multiplicity equal to 1. So if you apply the spectral theorem, then you will get algebraic multiplicity is also equal to 1. So hence, if the graph G is connected, then 0 is having multiplicity equal to 1. That means nullity is equal to 1, then rank of your graph L of G is equal to n minus 1. Okay. Yeah, so that's the proof of this case k equal to 1. Okay, for k greater than 1, I'm just giving this as an exercise. Okay, so this just you focus on each of the components corresponding to each component, you will get you will be able to do the same argument for each of the components. Okay. Suppose one component has n1 vertices, then you will get n1 minus 1, rank n minus 1 for that submatrix corresponding to that particular component. Okay, you apply this argument for each of the blocks and then use sum. Okay, then you will get the answer. Okay, so I will give you a reference for these proofs. You can go through over it if you are unable to prove it. Okay, let us go back to the problem. The bisection problem. So this is the bisection problem. So you have a graph V. Okay, you have a graph G with the vertex at V and its at E. Okay, so this is the standing assumption. I'm always working with the graph G equal to V comma E. So the problem is bisection. So here I have corrected that. So I want to partition the vertex set into two parts, V1 union V2, such that V1 intersection V2 is empty and the cardinality of V1 is equal to cardinality of V2. Okay, maybe for the time being you assume a cardinality of V is an even number. Okay, if it is not even, then you can go for the almost equality. Cardinality of V1 is equal to cardinality of V2 plus minus 1. Okay, up to one different we can go for. Okay, for the sake of simplicity, let us assume it's an even number. Cardinality of V is an even number. Okay, now, so remember what we did. I introduced the graph partitioning problem, then we jumped into the Laplacian matrix part. Okay, so now in this part, in this slide, I will connect these two problems. Okay, how to connect this vertex this partitioning problem with the Laplacian matrices. Okay, this is the one of the important part of my talk. Okay, so we are going to define a vector whose entries are either +1 or -1. Okay, depending upon the component, the coordinate I where it belongs to. Okay, so V is a graph on n vertices. Okay, V is a graph on n vertices. So each each component of this n vector. Okay, x is an n vector whose components are either +1 or -1. So each component of xi can be represented, can be associated with the vertex. Okay, so xi, I'm going to define it to be equal to 1 if I is in V1, -1 if I is in V2. Okay, this is your V. Okay, if you partition V1 here and partition V2, V1 is here, V2 is here, then the vector I'm going to associate it in this way. So all the entries of your vector x corresponding to the indices of V1, they will get 1 here, and all the vectors, all the elements of all the coordinates of the vector x whose indices are from V2, they will get -1. This is the way we are associating a vector with the given bisection. Okay, so I think it should be clear to you. I'm not calling this a bipartition. I'm calling this a bisection because between the vertices of V1, you may have edges. Okay, in case of bipartition, we don't allow edges between the vertices of the same partition. So here we don't restrict that. You may have edges between vertices of V1 as well as vertices of V2. Okay, that's one difference. Now let us compute this quantity x transpose Lx. Okay, this quadratic form. I said that this quantity is a very interesting quantity. Now it is going to tell you some interesting fact about or interesting connection between the partitioning problem with the Laplacian. So what is that? So x transpose Lx, you see. So this is the formula we already derived. Okay. So for this particular vector x, okay, for this chosen vector x, let us compute what's happening to this quantity. Okay. So what are the choices for xi and xj in this for this fixed x? You have two possibilities. Four possibilities basically. Xi can be +1 or -1, and xj can be +1 or -1. Okay. So when both xi and xj, if they are having same sign, okay, then this quantity will be equal to 0. So precisely when xi and xj are the same, okay, when xi equal to xj equal to 1 or xi equal to xj equal to -1, in both cases you will get 0 here. When those cases will arise? If both the vertices I and j, if they are in same component. Okay, so V1 is here, V2 is here. Okay, if your vertices I and j are in the same component, okay, then xi minus xj in this sum, that will be equal to 0. Similarly, if I and j are in V2, again you will get equal to 0. So you will get a non-zero quantity only when the vertices I and j are in different components. Okay, so now some of you might have got what I'm trying to say. So this quantity is nothing but, okay, so whenever they are in different component, what will happen? Again, I will redraw. This is V1, this is V2. Okay, whenever I have an edge from V1 to V2, let's say I and j, what is the contribution of this edge to this sum? Okay, so whenever I is in V1 and j is in V2, okay, so you will see xi minus xj. Okay, so xi is 1 and xj is -1, so you will get 2 here. So 2 square is 4. So corresponding to each edge, okay, which is having one end in V1 and the other end in V2. Okay, so you will get 4. Okay. And how many 4s you will get? So 4s you will get for these many times. What is these many times? So number of edges you have from V1 to V2. So we have converted our aim is to minimize this quantity, right? Our aim is to minimize this quantity. Now we are able to give up the equivalent quantity in terms of the Laplacian matrix x transpose x. So we have transformed the problem, graph theoretic problem, into a problem which involves a Laplacian. Our aim is to find a minimum quantity, minimum for this value. Okay. So that is equivalent to find out. We have to find out a minimum. We have to find out the minimum of this x transpose Lx, where this x, the vector x, runs over all plus or minus 1 vectors. Okay. So we are transforming this problem from graph theory to an optimization problem. Okay. So finding a bisection such that the weight of this E, Vi, Vj is minimum. Okay. So finding this partition, this bisection, okay, is equivalent to finding a vector in the plus minus 1 vector, which minimizes your quadratic form x transpose Lx. Okay, so this is a nice optimization problem, but unfortunately, this is an integer programming problem. Okay, so the vectors, this is the problem. So whatever we have written here, just we can rephrase it. We have to minimize this quantity x transpose Lx. Constraint is that x transpose 1 is equal to 0. This x transpose 1 equal to 0, this stands for the balanced constraint. Okay, so that means cardinality of V1 equal to cardinality of V2. That means number of xi's which are having 1, okay, is equal to the number of xi's which are having minus 1. So x transpose 1, simply it sums all the components of your vector x. So where you have 1 for cardinality of V1 times and minus 1 for cardinality of V2 times. When you sum them, you will get 0. Okay, this is just the balance constraint. And xi belongs to plus minus 1. Okay, that comes from our reformulation. Okay, and this is an integer programming problem. And if you know integer programming problem, that is another hard problem to solve. Okay, so now here we can relax this problem. Okay, so we can simply consider this as a quadratic programming problem in this way. Okay, so this is the relaxed problem. So I will keep all the constraints x transpose Lx equal to 0 or x transpose 1 equal to 0. But I don't want this xi to belong to only plus minus 1. I will allow this xi to belong to entire Rn with the constraint that the 2 norm of the vector x should be equal to 1. Okay, if you don't know what is 2 norm, so you just take the square of the components, sum them, and then take square root of it. Okay. Of course, when you see directly look at this problem, then you have to get here n over here, okay, or n you should get, but you can suitably normalize so that you will get rid of that n. Okay, this is the relaxation problem for this integer programming problem. Okay, so we have many interesting methods. We have many known methods to solve this problem. Okay, but here, fortunately, the one of the naive method which we might have studied in our BSc or MSc is called Lagrange's multiplier method. Okay, so we are teaching for our first year BTech students here. Lagrange's multiplier method, if you see, so if you have to compute a minimum or maximum of functions of a function of
Anjita, please mute.
Okay, yeah, that's better. Okay, so we are going to just apply the Lagrange's multiplier method. Okay, just I will put everything together in the slide. Maybe I don't want to run out of time. Okay, so the Lagrangian is given by, okay, first you will take the objective function. The objective function is x transpose Lx. Okay, and some constant multiple of the first constraint and the constant multiple of the second constraint. Okay, so this is just the Lagrangian, and then the partial derivatives of the Lagrangians you will find with respect to x and this lambda 1 and lambda 2. Okay, this is usual computations. If you do it, you will get these quantities. You have to equate them to be 0. Okay, so now we have one more nice property. X transpose 1 equal to 0. That is given in the constraint. Okay, x transpose 1 equal to 0 that we have. That will imply lambda 1 equal to 0. Why? You just pre-multiply by the vector 1 transpose here. Okay, or okay, so I should say what is this 1? This 1 is nothing but the vector E. Okay, all ones vector. This bold 1 stands for all ones vector. Okay, so now you pre-multiply by this vector 1. Okay, 1 transpose. And then what will you get? Here you will get 1 transpose E. Here you will get 1 transpose L and 1 transpose lambda 1 1 and 1 transpose E. 1 transpose into L. What's the role of what about this quantity? 1 transpose L is nothing but when you pre-multiply by this 1 transpose with a matrix, then it will just compute the column sums of the given matrix. Okay, and we already proved that the row sum as well as column sums of the Laplacian matrix is equal to 0. So this quantity is 0 vector. okay, or 0 transpose vector. So the first term will become 0 here. Similarly, 1 transpose into x. So just this is a real vector, so you can apply a transpose one more time. 1 transpose x, the whole transpose, that is nothing but x transpose 1. That quantity also will be equal to 0 here. So remember, lambda 2 is a scalar. You can bring it out and then bring out, and then you can do that. So only you will left with this 1 transpose 1 into lambda 1 is equal to 0. That will give you lambda 1 equal to 0. Okay, so that this is the reasoning for why lambda 1 equal to 0. Okay, and yeah, so if lambda 1 equal to 0, then what's happening? From the first constraint, you are getting Lx equal to lambda 2 times x. Okay, now you see, if the x solves your problem, okay, the optimization problem, then it has to satisfy this equation. This equation is saying something. You see, this is nothing but the eigen equation for the Laplacian. Okay, so Lx equal to lambda 2x. This is the eigen equation for the Laplacian L. Now, what is our objective? Our objective is to minimize this quadratic form x transpose x over the entire real with the vectors are having 2 norm. When you do that, what's happening? You just pre-multiply by x transpose, you will get x transpose Lx is equal to lambda 2 times x transpose x, and x transpose x, it's nothing but norm of x square, which is equal to 1. Okay, so we get x transpose x is equal to lambda 2. Okay, we want to minimize this x transpose Lx. Okay, so whenever this x is minimizing this quadratic form x transpose Lx, then this is becoming an eigenvector corresponding to some eigenvalue of the Laplacian L. Okay, and of course the lambda equal to 0, it will not work, because corresponding to lambda equal to 0, we had only one eigenvector, all ones vector. Okay, so now you have to find out the minimum of x transpose Lx, which is find out the minimum of eigenvalues, okay, which are non-zero. So that is which I had to, the equivalent formulation is I had to find out the minimum eigenvalue, we had to find out the minimum lambda 2 constraints are given by this one. Okay, so just I have written this equivalent problem in simply we can say you had to find out the second smallest eigenvalue corresponding to the Laplacian. Okay, so second smallest eigenvalue corresponding to the Laplacian and the corresponding eigenvector will solve this problem. Okay. Okay, so remember this is a relaxed problem. We are not solving the original problem because we know that is an NP complete problem. Okay, so we don't have any easy algorithm to solve any polynomial time algorithm to solve the problem. Okay, so this is just an approximate solution to the given problem. Okay, yeah. So I think I told this argument in the previous slide. As 1 is an eigenvector of L corresponding to the eigenvalue 0, so lambda 2 should be the second smallest eigenvalue. Okay, the 0 eigenvalue we cannot take, as we are interested in taking the bipartition. Okay, non-trivial bipartition we are going for. Okay. Okay. So in the next page I will present the solution to the heuristic. Okay, I don't call that as an algorithm; it's a heuristic. Okay. So before that, this lambda. Okay, maybe I will present the solution and then I will tell something about lambda 2. Okay, so we have started with the vertex partition problem, and we have transformed the problem into equivalent eigenvalue problem for eigenvector problem for the Laplacian. Okay, so now let us assume we have an efficient method to compute the eigenvector corresponding to the second smallest eigenvalue. Okay, there are many very nice numerical methods are there which will give you efficient solution to the second solution to compute the second smallest eigenvalue and eigenvector. Lancaster algorithm, many algorithms are there. You can apply any one of them and you can get the solution to this eigenvalue problem. Okay, so from there how to get the solution to the biquadrate problem. Okay, so this is the idea. So let x be the solution to the equivalent problem. Okay, as x is the eigenvector corresponding to the second smallest eigenvalue. Now you just focus on the components of your eigenvector x. Okay, they are all real numbers. Now you take the median of all these real numbers. Okay, so median will divide your the components into two equal parts. Okay, so depending upon the median, you just divide your group the vectors into two parts. The components of your vector into two parts. Xi bar defined into xi bar. Okay, xi bar you take it to be 1 if okay. So let me repeat. So x bar is the new vector I'm going to define. Okay, depending upon the magnitude of xi. Okay, so going to be 1 if xi is strictly less than m bar. Going to be -1 xi is greater than or equal to m bar. Okay, so basically, if xi bar is if it is equal to 1, then I will put it in v1. If it is -1, then I will put it in v2. That will give you the bipartition. Okay, so this is the answer to the approximate solution to the given bipartition problem. Okay, so I don't claim that this algorithm will always work, but it works for many examples, many instances. Okay, many problems. Okay, that's the beauty of heuristics. Okay, so you don't have an algorithm which will run for every problem. Okay, if that is the case, then this problem we will call that as a P problem, and but it is not the case. So we will not be able to give any efficient algorithm to solve this problem. Okay, but this type of heuristics one can define. Okay, so this is one of the application of Laplacian matrices. Okay, and I promised I will talk something about the second smallest eigenvalue. The second smallest eigenvalue, lambda 2, that says some that contains a lot of information about your underlying graph. Okay, so one property is the second smallest eigenvalue is different from 0 if and only if your graph is connected. Okay, note that irrespective of whether your graph G is connected or not, 0 will be always an eigenvalue. Okay, the second smallest eigenvalue, lambda 2, if you take, that will be a non-negative quantity, as the matrix Laplacian is a positive semi-definite matrix. So second smallest eigenvalue is a non-negative quantity. Okay, so that non-negative quantity is different from 0, or lambda 2 is strictly greater than 0 if and only if your graph G is connected. Okay, and in fact, the magnitude of lambda 2 will tell you how well your graph is connected. Okay, so to be precise, if I call lambda 2 to be A of G, okay, lambda 2, if we denote this by A of G, okay, this is the notation used by Fiedler in his seminal paper on 1972. It's called algebraic quantity. Okay, algebraic connectivity. Algebraic connectivity. So this quantity A of G, it is less than or equal to the vertex connectivity of your given graph, and all of you know the vertex connectivity is less than or equal to the edge connectivity. Okay, this kappa of G stands for vertex connectivity, and the lambda of G stands for edge connectivity. Okay, this algebraic connectivity, okay, this gives the lower bound for the vertex connectivity. Okay, that means that if your algebraic connectivity is really high, okay, then your vertex connectivity naturally it is high. By vertex connectivity, we mean minimum number of vertices you have to remove from the graph, so that the resultant graph will become a disconnected graph. Okay, so minimum number of vertices. So for that, we are able to give a bound in terms of eigenvalues of the Laplacian. Okay, so this was proved by Fiedler in 1972, I guess. And this paper, you can see these problems are these properties are used in the new field, the machine learning and artificial intelligence, like anything. Okay, so this is one of the main tool applied in ML and AI. Okay, the spectral techniques. Yeah, so maybe whatever the content I have seen, I think one can propose a course based on Laplacian matrices and applications. In a master's level, one can float a elective course on Laplacian matrices and their applications. You can find those many applications. Okay, so at the end I will give many references. Okay. Okay, so I think I started around 11:05. Okay, I have around 6 more minutes. Just I will briefly tell the second application. This is one of the major problem which you will see in machine learning and artificial intelligence. Okay, clustering problem. Okay, so the clustering problem is just you have a collection of data. Okay, Now you have to group the data into several clusters. Okay, with respect to some property. Okay. So how to define this problem? Okay. So it is a set of we are given a set of points x1, x2 up to xn which are given to us. Okay, and a notion of similarity measure. Okay, Sij. Let's assume this is non-negative. Okay, so what do we mean by that? So whenever I have two elements of these sets, let's say xi and xj, I do have a similarity. I know how similar these two objects are. Okay, so if you want to take a concrete example, you can think of these elements x1 up to xn as elements of the real n-dimensional space Rn. Okay, and the similarity measure you can think of as the distance between the vectors xi and xj. Okay, so now the similarity is nothing but the distance between the vectors xi and xj. Okay, so I want to find the clusters. Okay, so clusters means it's like the collection of, so 2 points will belong to the same cluster if they are close to each other. Okay, the close to each other is not well defined, so that we have to define some threshold. Based on that, we will be able to make that terminology precise. Okay, so let us do that. So this is our aim. So goal is the problem. Divide the data points into several groups such that points in the same groups are similar and the points in the different groups are dissimilar to each other. Okay, so in our previous illustration, in the Euclidean dimension, in the Euclidean space, if we take n points, if you take 2 points in the same cluster, they should lie close to each other, and if you take 2 points from the different clusters, they should stay away from each other. Okay, that's the problem. Okay, so surprisingly, you can use the Laplacian matrices again to give a heuristic solution to this type of problems. Okay, yeah, 3 more minutes, I'll be able to describe that. Okay, yeah. So first we have to associate a graph with this problem. Okay, so this association is very natural. So what do I say? So for if you have n points, then you draw a graph on n vertices. Okay, and you have to draw edges between any two pair of vertices. Okay, weighted edges you can call, and whose weight is given by Sij. This is one way of associating the associating a graph with a matrix. Okay, and so this is one way. This I have not written here. The second way is, or you can take exponential of that things also. Okay, the second thing is, we don't want to keep all the edges in our graph. Okay, so in order to skip some of the edges, what I will do, you know the similarity measure between any two vertices. Now I will set a threshold. Okay, so threshold means if I will give a value to u. Okay, if Sij is greater than or equal to that particular value, then you draw edge between these two vertices in the given graph. That is, simply if Sij is different from 0, then I will not draw edges between the vertices xi and xj. Okay, so I'll fix a threshold. Maybe you can take this to be some 1 or 2 or 3 and so on. If Sij is greater than or equal to that particular threshold, then only I will draw an edge between the graphs, between the vertices xi and xj. Okay, so in this way you can associate a matrix with a given graph. Now, so this last point is a more important point, which connects the vertex partition problem into the clustering problem. Okay, so the clustering problem is nothing but a kind of vertex partition problem. Okay, so you have to find out the vertex partition of the graph G such that edges in the different groups have low weights and edges in the same group have high weights. Okay, so this part I'm not explaining very well. Okay, because of time constraint, you read it and then you'll be able to convince yourself. Logically, this clustering problem and this vertex partition problems are closely related. Okay, and yeah, this is the last slide for my talk. How to do the clustering. The similarity measure, yes, we have taken. Okay, so this is an n by n matrix. It's a symmetric matrix. Okay, so suppose if I have to construct a cluster which consists of k points. Okay, or k clusters I want to consider. Okay, So cluster means group of points. Okay, suppose you had 100 data with you, 100 data points with you. Now you have to construct a cluster which consists consists of 10 components. Okay, so this k in this case stands for 10. This n will be equal to 100. Okay, so the algorithm is this one: compute the weighted adjacency matrix constructed from the similarity graph. Okay, this we have already explained. With respect to some threshold, you will associate that, and then compute the unnormalized Laplacian. This unnormalized Laplacian I have purposefully included here because there is a notion called normalized Laplacian. Okay, those who are interested, you can go through it. That is also found lot of application. That also contains lot of combinatorial information about the underlying graph. Okay, compute the usual Laplacian. We call this as a normalized Laplacian, and then compute first k eigenvectors. Okay, if k is the number of clusters you need. Okay, then compute first k eigenvectors u1, u2, uk of L of g. Okay, then you form this unitary matrix, this matrix U. Okay, whose columns are given by u1, u2 up to uk. Okay, remember ui's are n vectors. Okay, column vectors of size n. So this u1, u2, uk, if you keep them as a columns of this matrix U, then you will get a matrix of this type. Okay, then you focus on the rows of this matrix U. Okay, so let us call yi's to be the rows of this matrix U. You will get n rows. Okay, with the k component. Each of the vector is a k vector. Okay. And you can use something called k-means algorithms to cluster these vectors yi's into k parts. Okay, so k-means is one of the naive algorithms. This is very easy algorithm. Okay, or if you are for students of mathematics, this k-means algorithm it should not be a very tough one to understand. This is sort of relatively easy to understand. Okay, so now you cluster this yi's with respect to the using the k-means algorithm. Okay, so those clustering will give you a clustering for your given problem. Okay, that is we are going to form the clusters A1, A2 up to AK, where AA consists of all data points for which this new clusters Yj belongs to the cluster Ca. Okay, so remember, I'm not giving any proof. These are all heuristics. Okay, for under certain assumptions on your data, this algorithm works nicely. Okay? I think this algorithm maybe around 2,000 people started using. So there is a normalized version for this also. It was studied by Shi and Malik in 2001 or 2. Okay, which found some application in image segmentation. Okay, yeah. So that's all for today. I will just briefly tell you the references. So that most of the theoretical results which I discussed, you can find in Bappett's book on graphs and matrices. Okay, and this normalized Laplacian, which I didn't discuss today. If you want to know about the normalized Laplacian, this is the best source for the book for this concept of normalized Laplacian by Professor Chung. Okay. And yeah, this partition problem, what I had discussed today, these problems I have taken from some lecture notes. They were giving reference to this paper. Okay, I think these are the two first papers which discussed these problems. Okay, and these two papers by Mr. Fielder, these two papers are seminal papers. I think with your master's background, you will be able to study this paper. It's one of the fantastic. Both of them are very interesting papers to read. And just for like you go through, you see the number of citations of these papers in Google Scholar. I think it crossed 100, not 100,000, crossed 1,000 long back. In pure mathematics, getting more than 1,000 citations is really hard. Okay, so but the paper is really a fantastic paper to read. You will be able to read it and enjoy. Okay, and this is about. I think this is the paper where they have shown this. I think this vertex bisection problem is a NP complete problem. Okay, yeah. So the matrix theoretic results which I used in this talk can be found in Hahn and Johnson's book. Yeah, this is an interesting paper, a little bit above our head. Okay, so on clustering, good, bad, and spectral. So as I said, the spectral clustering may not work always. Okay, under what are all the assumptions on your data? This or on your given data, your spectral clustering will work. So those type of things are discussed in this paper. It's purely a mathematical paper. So with your MSc knowledge, you will be able to read. Okay. And as I said, this is a not an algorithm, so it should have always its own limitations. Okay, those limitations can be found in this paper. Okay, and through NG, yeah, I think if you are towards the MI and AL, you should know this name. Andrew NG, I think he's from Stanford. He's offering a lot of courses on AI. In YouTube itself, we can find. Okay, so this is an interesting survey written by them, interesting paper written by them. Yeah. So most of the content of this talk I have taken from this lecture notes. Okay. The partitioning problem, everything I have taken from this lecture notes. I think chapter 4 of this lecture note contains everything. Okay. You can go through over it. Just search for this name in Google. You will get that lecture notes. Okay. Yeah. So this is the last slide. So these two papers are like for planar graphs, the spectral partitioning always works. Okay. So these two papers are almost the same. And yeah, so these things, the spectral clustering, whatever I have explained, that version I have taken from this survey article. This is an interesting tutorial, interesting article, tutorial on spectral clustering by Ulrich van Luxburg. This very nice one. And this Vishnu is Lx equal to B Laplacian solvers. Again, this is a lecture note, and look at revisions. This is one of the fantastic lecture notes on graph partitioning, expanders. If you're interested in knowing about expanders, this is one of the very good source to study about expanders, and some more spectral methods also discussed over here. All these things are available in internet for free. You can get it done. Okay, that's all for today. I think I have taken 5 minutes extra. I'm sorry about it. Yeah, thank you so much. Other question?
Thank you, Dr. Rajesh. Now it's time for interaction. If anyone have any doubts, you can ask now.
Hello.
Yes,
Am I
yes.
audible? Hello, sir. I just wanted to know could you please mention the source for spectral sparsity that you've mentioned earlier?
Okay. So that's a paper by Dan Spielman. Spectral. I can put the link in the chat box. Spectral sparsification. Yeah. So the main paper which appeared in SciMax, not SciMax, is I think SciM Journal of Computing. Yeah, it's a 45-page paper. So this is the paper where this is one paper. Okay, the another thing is I think appeared in ACM. Yeah. So these two sources are contains almost whatever you want to know about this spectral sparsification.
Okay, sir. Thank you.
Okay. Yeah. Yeah. Are there other questions?
Any other questions?
Yeah, anything related to graph theory, this talk you can I can ask.
Students also can interact.
Yeah, please feel free.
You can ask any questions related to the institute, IIT, and any questions about your research.
So I think if you know how, so how many of you know how Google works? Google, how it works? Any idea? Okay. So that is also, you can consider that as application of spectral graph theory. Basically, you will associate a matrix with the collection of all web pages in the internet. Okay, and you have to compute the largest eigenvalue and the corresponding eigenvector. Okay, after doing some intermediate steps. Okay, so the spectral graph theory found applications in many fields. Okay, even if you are towards pure mathematics, let's say if you are interested in group theory or algebra, or if you are interested in analysis, harmonic analysis, everywhere the spectral graph theory found applications nowadays. In fact, so I can tell you a couple of places. The expanders which I was highlighting in Luca Trevisan's lecture notes, the construction of expanders is a highly non-trivial job. Okay, so more precisely, construction of Ramanujan graphs, which are highly non-trivial objects. So most of the constructions are coming from abstract algebra, representation theory. Okay, so this is highly kind of interconnected subject. It is connected to many other subjects, many pure subjects. Okay. Yeah.
Sir, is there any recent publication of books in Laplacian matrices?
Laplacian matrices. There is no new book as of my knowledge. There is a book by I think Bogdan. Okay, a brief introduction to spectral graph theory. That is, I think, 2019 or 2018.
Okay.
I know.
Okay.
Yeah. Yeah, from application point of view, so I mentioned one book here, the Laplacian solvers. You can see this book. This book also contains a lot of interesting applications of this Laplacian matrices. Yeah. And of course, I didn't mention some of the classics like Boe and Moher. He has written a survey on Laplacian matrices. In fact, he has written one more survey, eigenvalues of graphs and their applications. So where you can find some more applications.
Someone is asking the references. Can you share the references slides?
Yes. I will send the presentation to you after the talk. You can circulate the references. Yeah.
Okay, sir. Thank you. Any more questions? You may put it in the chat box if there is any question.
Yes.
We can wait for 1 minute if there are any questions are there.
Sir, I had one more question. Can I ask it?
Yeah, sure, please.
So I'm an MS level student. I actually, so I'm starting to work on spectral graph theory, and I've only learned up to advanced linear algebra. So I wanted to start learning on matrix theory. So what would be a good book to start with it?
Hahn and Johnson is the best book. Like it contains all the, it contains everything about matrices what you want to know. But it's a huge book. It consists of 600 pages. My suggestion is like you start reading the spectral graph theory directly. Whenever you need some tools from matrix theory, you can go back to the book and you can read those concepts from there.
Okay, sir. Thank you.
Okay, so that will be. Yeah, the Spielman has written a book. I think, yeah, maybe to Dr. Anu and others. So Dan Spielman, he has written a book on algebraic and spectral graph theory, which is yet to publish, but that draft version is available in his webpage. So,
Okay.
Yeah. So,
okay, sir. Thank you.
That is, we can put that reference here. It's from Yale University. So I can teaching.
One participant is asking a reference text for matrix theory.
Okay, so
Matrix Johnson is a good reference.
Theory by Hahn and Johnson. The first link is for the book, the algebraic and the spectral graph theory, and the second is the book by matrix. Oh, I'm sorry, matrix analysis, not matrix theory. Matrix by Hahn and Johnson. Yeah, spectral and algebraic graph theory, that's the draft name that can be accessed from this link.
Okay, if there is no other questions, I think we can end up this session. First of all, I thank Dr. Rajesh for an excellent and interactive session. I'm sure the session is very useful for the research scholars and a motivation for the students to do research. Also, it was a very nice and interesting topic, spectral graph theory. It is a combination of matrix theory and graph theory, which gains interest for researchers all over the world these days. Once again, I thank Dr. Rajesh for a very nice session. A feedback form is shared in the chat box. All the participants are requested to fill in the details there. Now I invite Professor Liju Alex, Assistant Professor in Mathematics, to deliver the vote of thanks.
Respected College Principal Dr. Steffi Thomas, College Bursar Father Philmon Kalatra, Dr. Rajesh Kannan, Department HOD Ms. Ann Jones, and the program convener Dr. Anu Varghese, and various faculty members in and outside the colleges, research scholars, and my dear students. Today we had our 16th lecture of the International Lecture Series Vykhari 2021, organized by Bishop Cholaparambil Memorial College, Kottayam. So without much further ado, I would like to propose the vote of thanks for this event. First, I would like to thank the organizers, especially the principal, BCM College, the Bursar, Father Philmon Kalatra, and the entire college management for conducting this wonderful lecture series, and also allowing us to be a part of this wonderful lecture series and providing with us everything to conduct this lecture series. Thank you. Next, I would like to thank Dr. Rajesh Kannan, who delivered a wonderful lecture in Laplacian matrices and its applications. And even someone who is not from a graph theory background can also understand in detail about the fundamentals of Laplacian matrix and its application. I'm also working in algebraic graph theory. So it's a wonderful session. Thank you, sir, for giving us a wonderful lecture on this and giving in detail about the various references. Okay, so thank you, sir. Thank you. Next, I would like to thank the department HOD, Ms. Ann Jones, and the coordinator, Dr. Anu Varghese, for effectively conducting and successfully coordinating this event. Thank you. And also, last but not least, I would like to thank everyone who has participated in this event, various academicians in and outside the colleges, various research scholars, various students. So I hope you all had a wonderful time, and I hope sir inspired you to pursue in a research or something in algebraic graph theory. So thank you all. We hope to see you in future events conducted by Department of Mathematics, PCM College. Thank you. Hope you all have a wonderful day. Thank you.